of all, you hopefully have seen the new assignment that has been posted. It's regarding basically k-means and exploring aspects of the k-means algorithm, as well as hierarchical clustering. It also has a visualization component. And the first question I think is very important, mainly because once you have that skill, the ability to sort of manipulate these visualizations, that allows you to do a lot more with clustering algorithms in the next few assignments. So then I can just say things like, okay, try these different methods and look at them and see what you get. So the first question I'm really hoping that you can spend some time on and make sure you are able to do the basic CA in that TSNE sort of modified version. Okay, so that's one thing that's going to be important. And again, playing with the hierarchical clusterings and just thinking about how you might make things work one way or the other, how you can change and shape the clusterings, especially since you have a visualizer, is kind of fun because again, a lot of what we do with these algorithms is trying to understand what kinds of clusters they tend to find. And playing with this is going to help you understand that for these particular methods. Okay. And also trying out different visualizations for k-means might be fun as well. Yes?
I have a doubt regarding the first question.
Yes.
Regarding the PCA part of it.
Yeah.
So what do we do? We take the eigenvectors corresponding to the highest two eigenvalues and transfer the multiplier and take that as the output to do.
Yeah, so you get basically the PC allows you to extract coordinates in a new space, right, from the data. And then you want to see what it looks like in this new space. The hope is that somehow your data has been transformed magically so that things that are close, truly close, are kind of pulled apart into one group, and things that are not close are pulled apart. But we have to see. And that's the point of the PC. And you'll find that the place where PC doesn't work very well. And that TSNE works a lot better. That's why you want to sort of try these different methods and see how they work. PCA is in some sense a linear method. So if there's lots of nonlinearity in your data, it's not going to really capture it. The second method is slightly better at capturing it. Nitin, did you post the blog post as well?
No, I did not.
If you can add that
Yes,
as a link, just so
I'll
people
add
can
that.
read that. So it's a very
Right.
good post on the different ways in which these things look, especially on MNIS. So
Okay.
give people a way to compare it with what they're doing as well.
Okay.
Usually, does not have implementation in C++ or Java.
It doesn't? I thought it does.
There were a lot of, okay.
In Python, R.
Okay, well, this is the kind of thing you're supposed to comment and we'll take a look at it. Because the reason we put it there is because we thought there were implementations. There aren't, then we have to go look. So.
Okay.
Okay, so we'll post a note in the discussion board and then we'll take a look at it. Any other questions on the homework? Okay. All right, so let's start today. We've seen, again, a number of different ways of representing data, number of different representations of data that might arise. And we've seen associated methods for clustering that sort of go along with those representations, right? So the three representations that we've seen so far, with maybe more than one algorithm for each of them. So we've seen a metric representation. What I give you is, again, a distance function that satisfies triangle equality, and I want to do something with it. We've seen a more embedded representation, which for now I'll just say is Euclidean. There are other ways of embedding it, of course, but this is the most common one. Which means not only do you have the distance function, you have this thing called a norm. And in fact, you have more than that. You have this Euclidean space, so it's got an inner product along with it as well. So it's got a lot of structure to it, right? It's just a distance function. And then we've also seen, in the case of spectral clustering, that you might have a graph. You might only have similarities between things. Right? So you have some similarity function, and you want to convert this, you want to build a cluster data using similarity. Okay. And we've seen different methods that work here. For example, if you're in the metric realm, you might use something like k-center or even k-median. You could even use something like single link hack, because it, again, all it uses are distances, so single link, even complete link, will work in this case here. So you have some choices. If you have Euclidean data, of course, the canonical example is k-means. You could do kind of average hack as well, because now you can define averages, centroids of clusters and things like that. And of course, if you have graph data, we've seen that you can do spectral clustering, which, as I said before, is more of an embedding problem than a clustering problem, because then you can think of spectral clustering as a mapping that allows you to go from here to here, right? Because what you're saying is that I compute this Laplacian, do this magic mapping on it, and that produces a new representation of my data that's not Euclidean. And once I have that, I can just run any algorithm that works here. So now you have this spectral mapping. And of course, once you say it that way, you realize, okay, maybe there are other ways of doing this embedding. I'm not limited to a spectral embedding. In fact, there are other ways of doing it. And you could choose what you want. It depends really on what you want. But the point is there's some way to get there. But there's also, of course, ways to go among all of these things, right? So this is kind of obvious. If I have Euclidean data, I always have a metric from it because I have Euclidean distance. This is kind of trivial. You don't have to do anything to go from here to here. This is a include special case. To go back, of course, is not that simple. You can't always do this. Sometimes you can. And if you can, you need something called a metric embedding, which we talked about as well. And you'll incur error in the process. You may not always get what you want. But the advantage of doing this is that maybe you can get it out and it works a bit more efficiently. Or this is better. So you have these ways of going back and forth. If you have a graph and you want to go to a metric, there's an easy way of doing this at first. So if we draw this arrow here, right? If you have graph data, and let's say you have distances in the graph, not similarities, and you want to go to a metric, you can just do something like shortest path. That's kind of easy. And if you have a metric and for some obscure reason you want to think of this as a graph, again, you may not want, sometimes it's useful to think of it that way. An easy way is to just replace this by a complete graph with weights on all edges. Again, it's not clear what this gives you, but you could imagine situations where you have a metric, you convert to a complete graph, you create a graph, and you do some kind of spectral method, you embed it here. There are lots of ways you could imagine doing this. And for some problems, this might actually be okay. It depends on the problem. But because going from here to here directly via metric embeddings gives you a different representation in Euclidean space than going from here to here via the complete graph trick and then going from here to here via spectral embedding. You get a different structure altogether. And so a certain amount of, you are afforded a certain amount of creativity in how you kind of move around these representations, depending on what you want. There's one edge that I didn't mention, which is actually a common edge that goes from here to here. And you might wonder, why on earth would I want to do that? I mean, it seems like Euclidean data is where you want to be, where everything is kind of good. Why would you always want to go back to a graph? But it turns out that there are places where you do, because, for example, suppose you have manifold data. So let me draw an example here. Suppose I have a bunch of points in the plane, and they kind of look like this. Okay? Then the Euclidean distance between the 2 points is not necessarily a good way of actually capturing their similarity. Right? So this is the whole manifold problem. If my data lies on a curved surface in space, then the distance measured in the ambient space, the straight line distance, is not a good representation of what the sort of semantic distance might end up being. And the whole area of manifold learning is how to deal with curvature in your space in some form. Either a curvature represented by the data or the curvature coming from the problem itself. Say you're doing clustering of rotations for animation. Then your rotations themselves live on a curved space, and you can't just use straight line distance between them. So dealing with manifold data makes it tricky to use Euclidean methods. You can't run things like k-means because now your value distance function is not well defined. And so what you'd like to do is say, well, they're on a manifold, I can somehow reconstruct the manifold from the data. And to do that, you need to understand the notion of a neighborhood. You need to basically say, okay, I'm not going to look, very far out. I'm going to make some small window around myself and look at only points in that window. Okay? And then I'm going to try and glue these little windows together to make a surface. And there are sort of sound topological reasons why you can actually hope you do something like this, depending on how big the neighborhoods are and so on and so forth, and what kind of shape you're doing. So in order to do that, you have to actually construct some kind of neighborhood structure from the data, from the points. In effect, you have to construct a graph. So what you do is you take your Euclidean data. So you have a bunch of points, let's say P1 to P. So let's say you have points P1 to Pn in RD. Right? What you want to do is convert them.
It's like a multi-way path.
Pardon me?
It's like a multi-way path.
Multi-way path. It could be a surface also.
Sorry?
It could be a surface. I mean, this is just 2D, but in general,
Yes, yeah, of course.
So some kind of rubber sheet to then sort of extract from it. Yeah. So what you want to do from this is construct, V1 up to Vn in some set and along with edges. So you want to construct an edge set as well between pairs of keys. That's somewhat captured neighborhood structure. And obviously what you'd like to do is say, okay, well, I want things that are close by to be neighbors, things that are far away to not be neighbors. And so one way you can do this is to say the weight of an edge connecting two vertices in my new mapping is, well, the easiest way to say is to fix some threshold, t, and say the weight of this is 1 if the distance between pi and pj is less than t and is equal to 0 otherwise. So you put a hard cutoff. So okay, if you're within some distance 1 of me, you're my neighbor, otherwise not. Okay. And you can construct a graph like this, and then you can now start looking at structures of the graph. You can actually take this graph into a Laplacian embedding on it. Because now what you're saying is that I want to reconstruct this geometry and not this straight geometry. Okay, so that effectively this will straighten out the manifold. But this is a very hard kind of threshold. It's very strong. It's like, how do I know t? It's a magic parameter. I'd like something a little bit smoother. So a common way to replace this is to say, well, I want some kind of graded, gradually decaying thing. And of course, when you think gradually decaying, you should think exponentials of some kind. And so the other way of doing this would be to say there's some kind of x minus distance between pi and pj. And maybe there's a scale term here, if you want. And if I make this distance actually the distance squared, the Euclidean distance squared, this expression here is called the Gaussian weighted Laplacian. So you're constructing a similarity matrix. Well, it's not the Gaussian weighted Laplacian. The Laplacian you get from this weight function is the Gaussian weighted Laplacian. So you take the sum of the diagonals and so on and so forth. And the importance of this construction here is that it gives you this kind of decay, smooth decay, and there are other nice properties of it. So this gets used a lot, for example, in manifold reconstruction, or even in surface reconstruction for graphics. But this is a way to go from points in a space that might have some underlying curved shape to some kind of graph that actually captures the curve shape. Okay, so this is a very important way of thinking about this. So you can think of this again, one example is the Gaussian weighting. You go from here to here, and that actually is useful. And notice that this mapping to this mapping will not get you back the identity map. Because what I'm saying is that I'm going to change my notion of proximity by using the Gaussian weighting. I'm going to make points that look not that far, actually much further away. So I'm going to stress things out, and then I'm going to go back and reconstruct it again. So this kind of cool trick goes from Euclidean data to Euclidean data, but in the process you hopefully have flattened out your manifolds. And again, hopefully. It's very hard to prove when and where this happens, but in some special cases. Yeah.
So once you have this plane, right, how do you actually then get this surface?
Get the surface?
Yeah.
So what you do is you first construct this, you get the graph, and then there are many ways. So one example is called what is called locally linear embedding. You look at a point, you look at a neighborhood or a combinatorial neighborhood, like it's one neighborhood in the graph, and you try to find a local matrix that embeds that points to preserve those distances only. And then you have to find a collection of such matrices. And so if you think of a curved surface, it's locally linear. Right? It locally looks flat. So you try to find this local flat operation that changes over the space. That's one way of doing it. There are other ways which are more global. You look at shorter spots along the surface of the manifold and try to use that to reconstruct a distance using MDS, for example. Right? So you can construct a global MDS on this. And there are other techniques. There's a whole bunch of them. So there's a whole class of methods that come under the category of manifold reconstruction that talk about this. So again, this whole direction, as always, is not about clustering, but it's about representations. Right? And then you run the clustering on the appropriate representation. Okay? All right. So it's good to keep this in mind when you're playing with the data, because you have choices now. You may have data that actually is Euclidean, but it may be in your best interest to sort of go do something else with it because of what you're looking for. That's something you should remember. The new representation we're going to look at today, to add to this list, is a variant on the graph representation. It's going to come out here. But it's got some interesting new features that somewhat change the game quite a bit. And the twist we're going to add here is that we're going to allow the similarity function to be positive and negative. In other words, you're going to be able to express both likes and dislikes about other points in your set. Okay?
But you could do the same, just transform the function a little bit before.
Uh,
If you know, I'm saying, if you know finite amount of, you have finite amount of points, you know what are the distances, you can just transform it from
Oh.
0 to something.
how do you transform?
I
So
don't
you're saying if I have this, I can convert to that?
I'm not, like, strictly mathematically you can. But
You can't, okay, so-
You can, but if you have finite amount of points, right?
I always have I have n points.
Yeah, if you have n points, you know the distances between the
I know
points.
this is
Then you most likely can get back to the, I mean, like, from plus minuses, you can get just to a positive, right?
Oh, but suppose I only give you plus minuses. I don't have distances.
Oh,
You see?
you only have plus and minus.
Aha.
Minus 1 and plus 1.
For example,
Oh,
or maybe
mine-
something more complicated than that. But that's all. I don't ever understand.
Okay.
That's what I said. It's a general graph.
Oh, okay.
Ah, that's the problem.
But that's completely different.
Yes. So again, you might say, well, why should I care about this? I can invent representations, for the next 10 years. Why should I care about this particular form of representation? What's interesting about this? So let me argue that there are a number of places where this might actually come up naturally. And in fact, let me ask you, do you think this is a natural representation? Do you think there's a place where this might come up organically from the data? Because that's what you really care about, right? There's some natural ways of thinking about data where this comes up. What do you think?
There's lots of data.
Yes?
Yeah, there's lots of data. Like,
Give me one.
I know, I belong to a community or don't, right?
Right. And this is a good point though. What I'm not saying is that there are likes and nothing. I'm saying there are likes and dislikes. So not only do you belong to a community, you hate everyone else. This is a stronger statement. Because liking your community and not caring about anyone else could be modeled just by a graph, where you have some edges but not other edges. Right? So this is more of an absence of information. This is an active hatred. which is a stronger thing to be saying.
You could then do this in science, you could do certain experiments, like whether certain proteins react or don't react.
Right, again, but don't react could mean don't react or could mean, there's a notion of agonists and antagonists, right, in biology, when you have a drug molecule. One where it encourages something, one where it actually inhibits something. That would be close to what you're saying. But encouraging something versus not doing anything would be just a zero. So this is one possibility. You were gonna...
Like if you have like upvotes and downvotes on certain, like a Reddit post or something, right?
Upvotes and downvotes, good, okay, right. So then you have only one way to express yourself, either yay or nay, right, yeah. Okay, good. So let's write some of these down. So we have molecular interactions. We have, but the upvotes, downvotes thing is again, what I'm trying to look at is pairwise operations. In other words, I have a pair of objects and it has a plus ones and minus ones. In your Reddit example, you have an object and it gets pluses and minuses. Can you give an example where you have pairs of objects?
Pairs of objects.
Yeah, it's not a single, that's the point,
Relate-
it's a bit of a graph. Yeah. So the molecular interactions is fine. You have, two, proteins maybe, or protein and a docking site, and you have some kind of bipartite graph of proteins and docking sites, and you can sort of look at that. It's not quite, but it's there, it's sort of all in the right space. But this example is not that.
But if you vote for a person, it means that you like him, but then it means you don't like the other one.
Yeah, but I'm only giving you two. I want a situation where I give you two things, and now you have to make a decision whether it's a plus one or minus one. In this case, is the pair is what is it? The voter and the politician, is that what you're saying?
It doesn't
But then I never do a negative vote for anyone. I don't vote. I just don't vote.
It's implied. It's okay.
Yeah, it's implied.
There are many examples in our field.
Please go give me one.
So whenever you ask for these brand perception surveys, you
Yeah.
ask Coke, Pepsi, and people say, I like Coke, I hate Pepsi.
People say that.
Yeah, this type of, so there are some analysis, I don't know whether that's covered in your areas.
Yeah.
We do this conjoint analysis.
I've heard of this.
The whole thing is about comparing these different pairs and
Yeah.
trying to figure out what are the latent utilities people have about different attributes.
I see. So you get basically positive or negative sort of conjoint.
You like or not. You don't
Not like
There
it.
are lots of variants of conjoint.
Okay, so basically, so let's say product preferences,
Product
pairwise product preferences. Okay. Right.
Mac versus PC, and there are a whole bunch of things.
So you're saying it is not as useful just to say how much you like a Mac, how much you like a PC. It's more interesting to say what is the comparative.
What is
benefit.
comparative?
I see, and that somehow is more because.
Yeah, because there is this whole area in economics about reviewed preferences.
Okay.
So sometimes to get to those reviewed preferences, either you see people behaving, or if you don't want to see people behaving and you want to get their opinion, you have to give these comparison points and ask them this thing. Yes, I like this, I don't like this.
I see.
And then you try to kind of extract that actual preference from that data.
Right, right. Okay, good. So in other words, what you're saying is that it has been observed that sometimes it's more effective to do sort of plus minuses to get at people what people are looking
Yeah.
as opposed to asking for ranks. Okay, that's very helpful. So that's another example there. And this was actually my first example, so asking if they like or don't like. So I've given people versus people, like the hot or not kind of thing. This is another way of thinking about it. So another example that comes up in clustering itself is what is called must link and cannot link constraints. So we haven't talked about this much, right? And we've always assumed that we can express everything we know about a domain for the purpose of clustering through its features, right? But of course, in any particular domain, the experts in the domain usually have a lot more domain knowledge that can be used to improve the clustering, but it can't always be expressed as some new feature. Maybe it can only be expressed in pairwise terms, where the expert will look at two things and say, no, these, I don't know why, but I know that these two really have to be together. This is what is called a must-link constraint. Or you can say, no, I have a lot of experience with these kinds of MRI images, and they really are not the same. Just trust me on this. I can't really explain to you why, but they're not the same. And so you want to capture the information from the expert, even though they can't quite explain exactly why. In fact, a lot of work in feature learning is basically trying to convert that more inchoate knowledge about things that should or should not be together into an actual feature. So in that case, you have what I call must-link and cannot-link constraints. And there's work in clustering on saying, okay, I want to do k-means, but in addition to all the representations, I actually have these constraints, and I want to satisfy the variance constraints like. So this, of course, is a plus constraint, this is a minus constraint. You want to have things that are together, you want to. So that just naturally comes up there. Another example is if you're looking at trends. So you can look at, so suppose you have a bunch of variables. Let's say you're doing stock ticker analysis, and you're looking at trends in variables. Right, so given any two stock labels, you can look at their correlation. You can find the correlation coefficient. It's usually some scaled version of xi, xj. And this is the number that varies between -1 and +1. Basically, if they grow together, there's a +1. If they're completely opposite, it's -1. And if they don't have any relationship, it's kind of a 0. So you get a number that's actually a weight somewhere between -1 and 1 for every pair. And now you'd like to say, okay, what stocks tend to sort of move together? They tend to grow together, and are they a form of unit? I mean, so if you want diversity, for example, in your portfolio, you don't want to invest in a bunch of things rather than go the same way, go down the same way. Right? And so what you'd like to do is cluster them by trend lines, where what you have is this much information about them, how they correlate in terms of their trend. So that's another example where you might see things where these are timelines, they're abstract objects, but you have this mapping. A final example, again, that comes from clustering, switch to blue because this is fading out, is the problem of when we'll talk about this later in the course, is called consensus clustering. And again, briefly, because I want to talk about this in more depth later, if you have a bunch of different clustering algorithms, they all capture some different kind of truth about the data. And what you'd like is to find, okay, where do they all agree? They might do different things data, but they all agree on some things, and I'm more willing to believe that those things are true about the data than the things where they differ. And so what I'd like to find is some kind of aggregate clustering, some kind of thing that takes a bunch of clusterings and puts them together in some way. Now you all remember the random index, you did this from the first assignment. You can ask questions like, for every, so I'm given clusterings, let's say C1 up to Cm on the data. And now I can say, take a pair of points x1. You can say in how many clusterings are they in the same cluster? So let's say it's some k. And how many clusterings are they in a different cluster? So let's say it's some m minus k. Right? Now, if you take the difference of these two, right, and you can normalize this by n. So let's say you do something like 2k minus m divided by m. Right, so you normalize this. This is the number between 1 and minus 1. It's 1 if they're always in the same cluster. It's minus 1 if they're never in the same cluster. So again, if you think about how to cluster objects, what you can do is take a bunch of clusterings, compute this pairwise matrix, cluster that pairwise matrix using an algorithm I haven't told you what yet, and then what you get is some kind of consensus. You're basically capturing consensus among these clusterings about which point should be the same. So there are many places where this idea of having positive negatives show up. And the problem of how to cluster with this kind of data, this representation, has its own name, and it's called correlation clustering. Unfortunately, there is actually a separate literature that talks about correlation clustering and means something completely different. It talks about subspaces in the data and looks at sort of linear correlations. So when you do, if you do look up correlation clustering on the web, be careful. Most of the time you will see this, but sometimes you will see a different kind of thing involving geometry and data. So if you're talking about, if you see people talking about subspaces and geometry and embeddings, you know you're not talking about this, because this has nothing to do with it. So here the input to your problem, so the input, again, is a set of objects, an abstract set, and some kind of function, which we'll call a similarity, which maps from V, and let's say for now, it's, some kind of function that takes two things and maps it to the set okay. And the goal is to cluster V. And of course we can come up with the cost function. So what do you think would be a good cost function?
I don't even know what clusters look like.
Oh, a cluster is always a partition of the input. That means partition
What
V into
points would
groups.
be together?
That's what I'm asking. What would be a reasonable metric of success? When this is the only information you have, where you know that plus 1 means you want them to be together, minus 1 means you don't want them to be together. What would be your... So suppose someone said, okay, I have this data, and I want to partition V into groups. What would be an appropriate cost function for this?
You want to maximize the sum
Of what?
of similarities of points within the cluster over all the clusters.
So let's say that our output
C1 to Ci.
is some clustering C1 to, let me not use that, that's perfect. Output is C1 to some number CR. What is the cost of this? Then we're going to say we want to minimize something. So what is the cost of this? So you're saying to, what do you want?
Well, you look at all the points within, let's say, Ci,
Yeah.
and you want to be all of them you want to be plus 1, right? But most of them should be plus 1.
I know. Okay, so,
And
good. So what's
it's
the
a sum over the point, over the pair of points.
So it's a sum over I equal to 1 to R. Okay. And a sum over all pairs X, Y belonging to Ci of a 1 if they're similar. So it's a 1, which is a characteristic function. This is one proposal for a cost function.
Yeah, but we can also measure now to the other clusters. So
Pardon me?
to all the other points, we want to have a minus 1, right?
And to all the other points, you want to have minus 1. Okay, so you want to add, again, for all points, for all j, such that I, comma j not in same cluster, you want to add up the counts of things that have a negative value.
But I don't think you can differentiate this.
Huh?
It's very hard to achieve. It's
That's not our problem yet.
It's too hard to run.
That's not our problem.
No.
Our problem is not, in other words, to figure out how to solve it yet. Let's first figure out if we like the cost function at all. There's no point wasting time optimizing something we don't like.
That is simply NC2.
Sorry?
It's simply NC2.
What is simply NC2?
N choose 2.
This whole thing? No, because this number does not fire unless the similarity is 1.
I'm telling you, some of them both.
No, because for pairs that are in different clusters, you only fire if they're -1. For pairs of the same cluster, you only fire if they're 1. So if you put a bunch of pairs together that are -1, you don't count anything. It's a 0 count. So presumably you want to maximize this quantity. Right? Okay. So this is what is called maximizing agreement. What you're trying to do is maximize the agreement of the clustering with the thing you set out. So we'll call this a max agreement problem. Okay? And this is one of the 2 variants of correlation clustering. Okay. Yes?
Would it matter how many clusters there are?
Aha! It doesn't.
Okay.
And this is a very important point. So I want to spend some time
So
talking about
there's
this.
one really nice property about this. It's like, if I were to choose where to put a point, if I have 2 clusters, right?
Yeah.
I would put it in the one that has the most agreement. That would be the output. It's like, you know, that's the term. If I have 2 clusters, and I have an option to put a point here or here, I will put it in the one that will maximize the function,
Mhm.
which means that we'll have the most agreement with the cluster.
Mhm.
So more points here and less negative points here, or either otherwise.
Yes.
It's just a property of this.
True. So that's true for nearest neighbor as well. If you take k-means, you put a point in this nearest cluster, that satisfies the same property. It maximizes your quality or it minimizes your quality. I mean, it's true. I'm not saying it's not true.
Yeah.
But in fact, I think there is something else that's going on here that distinguishes this approach to doing clustering from everything else you've seen so far. And I want to spend some time talking about another actually define this. The key thing here, in my view, and this is just this is a bit more of a personal opinion thing, right, is that, as you've noticed, it doesn't seem to matter how many clusters you have. And this is something that's very, very interesting here, because what it's saying is that this cost function is not monotonic. Okay, so what are we saying? What is the problem? So let's go back to our, previously on clustering. Let's go back to this choosing k problem. Why did we have a problem with choosing k? Why did we have to spend all this time and effort to choose k or to avoid choosing k somehow by using Hank? The reason was that the clustering problem in itself was not well formed, in that you could always split a clustering further and further down to smaller pieces, and your error notion would just get better and better and better. And there was no way to stop till you got to everything in its own cluster. You had to have some other way of talking about the meaningfulness of a clustering in terms of compactness or information theory or what have you, or description of bias, variance, trade-offs, and all that nonsense. Right? And that's because the error function itself was monotone. It always got better. So you had no way to stop it. But here, this error function is not monotone. It has bumps. So in particular, if you let's say you have 3 things. Plus one, minus one. So there's no way to make yourself happy with this. No matter what you do, you're going to have some, you're not going to maximize all the variables. Right? You can try whatever you want. Put them in separate clusters, what you want. The thing is that if you didn't have the notion of plus ones and minus ones, right? Suppose you only had minus ones, right? You only had notion of distance, things should be far away, and you put things far up in their own cluster. It's like it's fine. You don't. There's nothing wrong with this formulation. You have you keep things far apart, and other things you just don't care. And this is the issue about don't care as I talk. But here, because of the plus ones, you are actively losing profit from separating things that could have been in the same cluster. or you're actively penalizing yourself by putting things together that should be separate. So there's kind of this two-way dynamic here, pulling you and pushing you, right? That none of these other methods have. Because they're all based on notion of, okay, things that are farther are worse. They're not saying that things that are closer are better in some sense. They're just saying things, the further you go, the worse it gets. It's a one-directional thing. Whereas here, there are two different directions pulling it. Okay, now this is more of an intuition. This is not a formal statement in any sense. But one of the reasons why I think with correlation clustering itself, you have this non-monotonic behavior in the cost function is because you have this dynamic here pulling things apart. So you don't have a steady sort of, this always gets better if you go. And that is very, very important because I don't care what this is. For a given clustering with a certain number of clusters, I can define the cost function. But maybe for a particular problem, the best answer is to put them all in one cluster. Maybe for a particular data set, it's best is to put them all in separate. I don't have to care about it. And this is one of the most attractive properties of correlation clustering. It truly does not have a parameter, unlike everything else. Again, it's limited because it uses such an abstract representation. You could ask yourself, well, I would like to have correlation clustering for Euclidean data, and that's a separate problem. But in this setting, you don't have to worry about it. One question you could also ask, and maybe you have thought about this, is that the fact that I've changed my similarities to be positive or negative does not mean necessarily that I can't use the Laplacian approach, the spectral approach. After all, the spectral approach really says I have weights on my edges. It doesn't require the weights to be positive. So if you remember how the Laplacian approach works, what it says is that, so how do spectral methods work, right? So we say that we have this graph, G, and you have some weight function on the edges. Right? So R, again, weights could be positive or negative. So then you construct this matrix. So you construct the matrix D, which is for each, it's a DII is equal to sigma over all J Wij. And then, of course, the A matrix is basically just the collection of all the Wij. And the Laplacian is equal to D minus A, at least one version of this, right? And then we said, oh, wait a second. Now we can compute the eigenstructure of this matrix, and all the eigenvalues are real because this matrix is positive definite, and that's all good. And the reason we knew this matrix was positive definite is because we know that you can write X transpose Lx for any X, once you solve this whole thing, as what? When you remember this. What is the, if you wrote a Laplacian and did X transpose Lx for X in some vector, what would you get? Remember? Between all of two lectures.
Lij, like Lij and then Xi, Xj.
That's, yes, but that doesn't tell us that it's positive definite.
Oh.
You can write it in another form in terms of Wij's. Do you remember what that is? Is it in notes? It's Wij.
Yeah, times Fi minus Fj squared.
Right. And I said, aha, this is positive. But why is this positive? It's positive because at least when we were first talking about spectral methods, we said, okay, let's just be a graph. So these are ones or zeros. So these numbers are always positive. So this is always positive, therefore this is positive. If the weights can be negative, it's no longer obvious that this is positive. It may not be positive. If all the weights are negative, this number will be negative. Then this matrix is no longer positive definite. If this matrix is no longer positive definite, you no longer can guarantee that your eigenvalues are positive. And then the whole theory we built up around this breaks down. You have the eigenvectors and eigenvalues and everything else. So we might have thought we could use spectral methods to solve clustering in this +1 -1 setting. But it's not clear you can. I'm not saying you can't. It might depend on the problem. But in general, you can't. In fact, there's a sort of a unique characterization property saying that this matrix is positive definite if and only if there's Euclidean embedding out. It's a very strong statement. Okay, so they're actually the same thing in some sense. They're not really any different. So this is definitely more. So this is more general. It builds up from the graph, but it's more general because you can't do these kind of tricks. Yes.
I have a question. I didn't understand before. So that for correlation clustering, the K doesn't matter.
Yes. No, there is no K. You don't have to specify a parameter K.
What do you mean by that?
I mean that I can define a problem to solve and this problem does not have a trivial answer. Well, I could do the same thing for k-means. I could say, okay, for over any clustering, define the cost function, optimize the cost function. My answer will be trivial. Put everything in the cluster by itself.
Oh.
I have to fix k to hold that cost function so it doesn't go crazy. Here, I don't have to do that. That's the beauty of this.
So it seems like initially when you fix k, in other clusters, on correlation cluster, you have k, you have to fix the k.
Yes.
So the cost function there is monotonic, right? It always decreases.
With k, as k increases, usually, yeah, yeah.
But
Here
here
it's
you
not
have
true.
one more term here, the plus and minus. So
That's
it's like
right.
pulling and then pushing it here. So somewhere like
There's some
controlling,
sweet, there are bumps in the middle.
yeah.
Yeah.
I mean, the cost function.
Exactly, exactly.
Yeah, but who said that the cost function k-means should be just as simple as you said? Put everything in one cluster and that's good. We can put the compactness there as well. And then that optimization.
Yeah, but you do, but then you have to write it, right? I mean, how do you say that?
Yeah, you put in one optimization function, you have the part of.
No, but see, yes, you can say that a duck doesn't have to look like a duck, it can look like a cat, but then now it's a cat, it's not a duck anymore. I said k-means has this problem. If you know k-means thinks something else, then you can work very hard to say, okay, does this new thing capture what I want? And yes, you can talk, people have done this. They've said, okay, let's look at compactness criteria, let's look at between cluster width, intra-cluster width, do all kinds of crazy stuff. You can do that. They're all ad hoc choices. They're not sort of organic to the question. This is the only one I know of where it just naturally falls out of the question. You're not doing anything extra. And everything else, you're putting band-aids on this, sort of fix a problem you created. Here, there's no problem to fix in the first place. That's the difference.
Yes, that's
Yeah.
absolutely true. That's really nice.
Yeah, it's because of minus one, right? Because I think somehow.
So, till today morning, and for like 2 years now, or 3, I thought it was because of the minus ones. Now, I think it's because of the plus ones. So here's what I was trying to make an argument about why the minus ones mess everything up. And I'm not sure I can make one. I think you have, it's having them both in combination is what causes problems. If you get only minus ones or only plus ones, you won't have a problem.
Yes.
The push-pull effect.
Well, earlier we had pluses.
Yeah, sure.
We didn't have minus.
Right, because minuses are like distances, and distances are fine anyway. Right? So, yeah. Okay. You can actually, there are basically 8 different flavors of this basic formulation. The first variation, so there are 3 different things that each can change to something or the other. And so let me make a little table here. So the first way in which things can change is, are you, and I was referring to this here, either you're maximizing agreement or you're minimizing disagreement. Which is the exact opposite of this, right? You penalize all the things in a cluster that are -1, and you penalize all the things outside a cluster that are +1. And hopefully you're all holding in protest inside at this point, because these two look like exactly the same problem. Yes? This goes back to what you were saying, by the way. The sum of these two is n choose 2. So 1 equals n choose 2 minus the other. So why should I care about them separately? Can anyone explain this to me? If I have these 2 cost functions and their sum is a constant, why would I care? Obviously, maximizing one will minimize the other. Why should I care about them as separate entities? And in fact, why are there separate algorithms for these?
Does it depend on what question we're asking? Like,
It depends from which side you're approaching it, right? From how you're optimizing.
No, but one is one minus the other. If I optimize this, I'm optimizing that.
Okay, but you have different, maybe, approximation errors for those algorithms, so.
That's the point.
Yeah, that's what I'm saying.
In the exact setting, when you want to find the exact answer, they have the same problem.
Yeah.
But this problem is NP hard. I mean, you can show it. It's not hard. It's not surprising. It's not hard to show. It's NP hard. Okay. So you can't actually solve this problem exactly. You have to approximate it. And then it matters a lot. And if you're not used to thinking about this, if you're approximating a number that's basically very big, it's kind of easy. Because if your optimal solution is 100, then as long as you're within 110, you've got a good approximation. But if your actual answer was 10, you need to get within 1 to get the same approximation. So it's hard to approximate a small number. It's easy to approximate a big number. Of course, if one of this is big, the other one's going to be small. And this is a very common problem in the theory of algorithm design, where you have two measures that are complementary to each other in this fashion. The total sum is a constant, but solving one is a lot easier than solving the other. Just the way these things work. So in fact, depending on which way you go, you have different algorithms and different qualities of approximation, different answers. So that's one axis of discussion. The next axis of discussion is whether you have weighted or unweighted. I said that you want to map these things to plus ones and minus ones. You could, or you could have weights. You could have a weight going one way for ij, and you could have another weight, so a negative weight, plus weight and a negative weight. And you could imagine that this will change things a bit, right? Because if you're, in some sense, this cost function is linear in the weights, so that's not a big problem, but the way you approximate it might change. And in fact, you often have to put some constraints on this. For example, if your weights are plus one or minus one, you can think I have a total budget of emotion to express to my other friends, right? To any other particular other friend I have. Either I can give them a plus one or a minus one, but the magnitude of my emotion is one. So you can say, okay, I can have a plus one and a minus one, a plus and a minus values, but the sum should be equal to one. You can think of this that way. Right? So for every pair, there is a plus feeling and a negative feeling. And you can now you have just balance these things out. It's not just a plus one or a minus or a minus one. So it's a more general representation of this. And there are other ways you can generalize this notion. So based on whether you have unweighted problems or weighted problems, again your solution will change. Okay. And finally, and this is a bit more subtle of a point, it also depends on whether you have complete information or incomplete information. And here's what I mean. So I said that the similarity function is a function of pairs of objects. So I assume that for every pair, I have a label, and let's say it's plus one or minus one. But maybe there are pairs I don't have access to. Maybe I don't want to store all the pairs. Maybe I can't store the pairs. Maybe I have a million people. I can't actually ask every pair of people in the group, well, do you like each other or not? So this either similarity function is complete, so it's defined on the complete graph, or it's defined on some subgraph. So you only have partial information. So you have likes, dislikes, and I don't knows. And that changes things as well. Because now the I don't knows could go either way. And you don't really know what's going to happen. Sometimes people say, I will just toss a coin and put a label on it. That's fine, but it changes your problem. So these three, you can imagine any combination of these 3 bits. So there are basically 8 different formulations of this problem. And they all have their own subtle variations. So obviously we won't want to go through all of these things. But I do want to spend the rest of the time we have with some simple, very, very surprisingly simple algorithms that do surprisingly well. Again, this is continuing our theme that you can do fairly complicated things here, but there's some very simple tricks that get you very far in solving these various experiments. Yes?
Are you sure if you go from plus one to minus one to weight, this convex combination of that the problem doesn't change it at all?
I didn't say that. I said, in fact, it can change a lot.
Yeah,
That's
exactly.
what I said. Yeah. Changes quite a bit. Okay? All right. So let's talk about some algorithms now, right? How do we actually go about, now we put all this build up, we've understood the landscape of these questions, how do we actually go about solving such a problem? So let's think of an easy case. The easy case we're going to think of right now is max, comma, plus 1 minus 1, comma, complete. The 0, 0 case. It turns out there's a very, very trivial algorithm, which is almost like so trivial it's kind of silly. That will give you a 2 approximation to the best answer. In other words, your answer will be within a factor of 2 of the optimal solution in this configuration. So it's very trivial. It's basically the form, do this or do that and see which one is better. So my question for you all is, what is this and what is that? For those of you who want clues, one possible somewhat cryptic clue, as I am known to provide, is max cut. For those who don't know, don't mind. It's not necessarily an alpha. So what do you think? Something really, really simple. So don't try to get fancy.
Create a flow model.
Huh?
Create a flow model by.
Create a flow model. Okay, well then what do you do that? Sir?
Just asking if you be creating a flow model.
Not in the solution I had in mind. Maybe your solution does. There's no shortage of solutions to this problem. Yes.
Oh, I was
Are
thinking.
we allowed to let the TA answer questions? Okay, fine.
And I don't know about
Okay,
this.
fine.
Yeah. So, I was thinking, what if we find the max cut of -1 edges, and then
So,
keep separating.
okay, interesting. Explain this to me more. So what you're saying is look at only the edges that are labeled -1,
and then
that's
find
a
out-
graph.
Yes,
Find a max cut in that graph.
right.
Okay,
And
good. And then
keep
what do you
doing that. So that would separate the graph into two.
But if you look at the -1 edges, though, you don't want any of them to be with anyone else. So then you want them all to be separate. So if you look at all the edges that are
Right,
-1s, right?
right.
You don't want any of those pairs to be together.
Right.
Okay, good. So you want to put them all separately. So now what?
So we get kind of two. Two
So now your
partitions.
vertices all separate out in some sense.
Right.
And any vertex that has any -1 edge attached to it becomes a separate isolated component by itself.
Mm.
You're about halfway there. When will this fail?
It's going out of my imagination.
You got about half of the algorithm right now. So here's the idea. So there are edges that are positive, they are labeled plus, and there are edges labeled minus. Let's call them E plus and E minus. Okay? So this is the algorithm.
So,
Of this.
so okay, maybe this works. So you select an edge with positive. Okay.
Some edges positive.
Yeah.
Okay.
And you put those two
Together.
together.
Okay.
And then you repeat.
Take another pair of edges.
Yeah, so
another
then-
edge that's positive.
No, then when you join these two, right, the graph slightly changes.
Yes.
Okay.
But now, this do I have a super node here? When I take that edge and collapse them?
Yeah, and nodes become, two nodes come together, yeah.
Because what happens when this vertex had a negative edge to something and that one had a positive edge to the same thing? When I collapse, what do I do with that edge? Do I keep it positive or negative? Or do I make it 0, in which case now I don't need to handle 0 edges? What do I do then?
They cancel each other out.
So you get 0? So you remove the edge, what do you do then?
On this step, they cancel each other out, but on the later stage, they may not.
That's the problem. So I'm asking what you do in that case. Or what do you think you might want to do?
Store the information for later stage, or just guess. I don't know. Like maybe two approximation, it doesn't matter. But
No, but you have to prove that you're going to do approximation.
I'm sorry.
You have to prove that you're going to do
Yeah, I know. I'm just saying maybe.
So it doesn't matter that you have to, what choice you make. Was there a hand up somewhere else? Okay, so here's the algorithm. So, count the number of edges that are positive and negative. If the positives win, put everything in one cluster. The negatives win, put everything in a cluster by itself. This is a true approximation. I told you it was simple. You see why? You see why it's a true approximation? For maximizing agreement, not minimizing disagreement. That's very important. So why is it a true approximation? Because if the number of, so obviously the total number of edges is the maximum number of agreements you can get, possibly get, if you're really, really clever. Right? You can't get more than that. If the number of positive edges is more than the number of negative edges, then this has more than half the total number of edges. Again, if you've heard of max cut, this is going to be familiar to you. So if you put everything in one cluster, you get the profit from all those edges in that cost function. So you get a profit that's at least half of the total number, right? So the profit, so in this case, the profit is greater than or equal to total number of edges divided by 2. But the total number of edges is greater than the optimal solution. Right? And so this is greater than or equal to opt over 2. And you get your 2.5 approximations in that maximum. Well, what about if the other way around happened? If the other way around happened, then the negative edges are winning. And now you're putting everything in its own cluster. You get all the profit from the negative edges. And we know there are half of them. 2 approximations. Completely trivial. And also not very interesting, right? Because it's saying there's no interesting structure that has come out of this. Right?
Plus 12 minus 9 complete.
Sorry? Pardon me?
How would min plus 1 minus 9 complete? That combination look like?
Min? It doesn't work. Because now you need to reason about the optimal solution. For maximizing agreements, I could say the optimal solution is at most number of edges. For minimizing disagreements, you need to be much cleverer. Because the reasoning about the optimal solution is a lot harder. And we'll get to that in a second.
Same algorithm.
The same algorithm won't work actually. Because you might have a lot of, you will end up with a lot of disagreements here. I just don't care about them. What I'm saying is, when maximizing agreements, there's a lot of agreements to be had because the number of edges, there's a lot of good edges. So this is a true approximation that's kind of silly. You actually can do a lot better. You can get an arbitrarily good approximation. So what you can get is a p-tas, which means I can get a 1 minus epsilon approximation. So I should call this half really. It's a maximization. So you can get arbitrarily close to a good answer. The algorithm is a bit more complicated, so I'm not going to talk about that here. But you can do pretty well in this special case. This is about the best you can hope to get. For those of you who care about such things, it's singly exponential in epsilon. It's not very bad. So for the simple case of maximizing agreements with plus ones, minus ones, and you have a complete graph, and actually I think this is true even if you don't have a complete graph, because the reasoning works the same. You're reasoning about the total number of edges. I have not used the fact that the total number of edges is n choose 2. It just happens to be the total number of edges. Right? So the true approximation will still work. The p-tas will not work for technical reasons that I want to get into. But the true approximation works. So you can still get a half approximation in the case when this is incomplete. So that's the easy case. But now we come to the more interesting case of minimizing disagreements, right? Where you have to think a little bit more carefully about what's going on. The algorithm ends up actually being quite simple, but you have to think more. So let me draw a particular widget here, because this widget is going to be interesting to me. So let's consider 3 objects. And let's say you have a plus 1 here, and a minus 1 here. As I said before, no matter what you do, you're going to pay a cost on this. You're going to pay a cost of at least 1 for this triangle, no matter how you partition it. You can check this for yourself and see. So in some sense, these objects like these give you a lower bound on the optimal number of disagreements. Because you have to pay at least 1 unit for every triangle that looks like this. And in some sense, well, no, I don't want to expect you. Anyway, so in some sense, if you want to minimize disagreements, you've got to get a handle on how many of these kinds of objects there are, and can you reason about what your algorithm does in relation to these things. Okay. And so on that note, let me give you another very simple algorithm that tries to optimize the disagreement. So let's draw that case here. So we're going to do min plus 1 minus 1 And again, it doesn't have to be complete, so it could be anything you want. And let me give you a simple algorithm that works in this case. We'll warm up with a simple algorithm that works in this case for 2 clusters. So let's say, I said that you don't care about the number of clusters with correlation clustering, and that's still true. But let's just say for now, that over all possible answers, I look at all the ones that have 2 clusters in them. And I want to find the best one of those, just for argument's sake. I'm not saying this is something we really care about, it just helps build intuition. So how do you find the best solution with 2 clusters? Right? This may not be the best solution overall, but it's the best you can do. And the algorithm is something like this. For each V, so construct a 2 clustering where C1 is equal to set up all U such that similarity from V to U is equal to +1. So all the plus neighborhood of V. And C2 is equal to V minus C1, everything else. Okay? And then compute the cost. Take the best cost solution. You can think of this as a very simple dynamic program, where you have a very simple structure for your clustering. You just take a vertex and all its plus neighbors, and then take everything else as the other cluster. This is not the only way to construct a 2 clustering, but this is just a particular set of them. And I'm going to take the best one of these. And the claim is that this is a 3 approximation to minimizing disagreements. And again, it helps to understand why that is. And so I want to sort of briefly explain how this proof works, just to get a sense of what's with this. You're going to see sort of sign hits of this technique in a more general algorithm that works for arbitrary number clusters. So I just want to go through this a little bit now. So do you understand the algorithm? The algorithm is basically take any vertex, or in fact do this for every vertex. Take the vertex, get its plus neighborhood. That's one cluster, everything else is the other cluster. Compute the cost of the disagreements. Write down a number. Take the next vertex, do the same thing, write down a number. Look at all your numbers at the end, take the vertex and give it the best number. Okay? And that claims that this is a 3 approximation. So within a factor of 3 of the optimal number of disagreements. Again, a very simple trick. And the basic idea of this proof goes something like this. Let's see. So there is some optimal solution which partitions the data into clusters. So it's called opt2, because we have 2 clusters. And let's say an edge is bad if it disagrees with opt. So what does that mean? That means that either opt put 2 things together that have a -1 with them, or opt put 2 things apart that have a +1 with them. So let's say the edge is bad if the edge disagrees with what the optimal solution did. Right? Obviously the total cost of opt is the number of such edges. Right? The number of such disagreeing edges is the number of disagreements, which is the cost. So we'd like to understand what the total number of these things could be. The total number is in fact opt, but we want to read them. Okay, so suppose there is a vertex that has no bad edges. Okay? All the edges emanating from this vertex are good. You're going to pick that for your answer. Okay? So that's a sort of a good case. You don't have any disagreements. Or you have very few. So in general, let's just say the vertex, let's say that the vertex has the smallest number of bad edges going on. It's called bad degree. So let's say the min bad degree. The min bad degree of a vertex is equal to B, let's say. So that means every vertex has some bad edges going on it. And of all of them, the one which has the fewest bad edges going on it has B bad edges going on it. Okay? Now, if the min bad degree of a vertex is D, right, then what you can say is that let me see if I can say this right. So what I want to say is that there are at most n times d bad edges overall. In the clustering that you get. Let me see if I can say that correctly. Hold on. Yeah, okay, so here's what we do know. If the main bad degree of vertex is D, the total number of bad edges is greater than or equal to n times D over 2. And remember, this is odd. Right? So the main bad degree of vertex is D, then every vertex has at least D things that are bad coming out of it. So the total number of bad edges is at least this much. Okay? Now let's say we construct a clustering where this vertex is chosen to be in one cluster. So this is put in one cluster with all these D things coming out of it. And everything else is a different clustering. Okay? So then what I want to say is that the total cost of my solution in this particular string I picked is equal to maybe opt that I pay anyway, the number of bad edges, plus some extra bad edges that I have to pay for that are going across these things. So let me just think about this for a second. If I take this and it has degree D, okay, so I'm missing a step here. What I want to say is that the total extra cost I'm paying, the total number of extra disagreements I'm paying, so the extra disagreements for this particular clustering that I picked is less than or equal to n times d. And this is a step I'm not quite sure why I'm saying, but this is what we need. In which case, we know that this is less than or equal to 2 times opt, because opt is more than n times d. And so if the total amount you pay is opt plus 2 times opt, and so your total cost is at most 3 times opt. So you get a 3 approximation. So this is not a very satisfying statement because this is one murky step that I've not moved. I will check this and sort of post a note clarifying this point. But at any rate, what you're able to show is that you can get a reasonable approximation in this 2 case just by picking one vertex and looking at its neighbor. So then let me actually give you a real algorithm for minimizing disagreements regardless of number of clusters. I want to prove the result a little bit tricky, but I'll give you the intuition for why this works. So this algorithm is called random pivot. And it looks like this. So it's a recursive algorithm. And what it says is, pick. So this is very much like a quicksort type method. So pick a random pivot. We're going to call it pivot P belonging to B. Okay? And then set C equal to, again, the set of all U such that B comma U belongs to the positive edge set, just like before. Okay? So you've done that, you picked up random B, and now you say, okay, now your answer, your solution is going to be C and random pivot, so it's recursive, on B minus C. So in other words, you peel off clusters one by one. Your algorithm is take a random point, take all its positive neighbors, put that in a group, repeat. So I read it recursively, but really just like this. And the claim is that this is a 3 approximation to minimizing disagreements in the same setting, but without regard to the number of clusters. It just gives you the appropriate number of clusters. Notice this algorithm will just keep going as long as there's stuff to pick. There's no specific thing saying, oh, you need 2 clusters, 3 or 4 or 5. It'll just keep going. It'll just keep peeling off stuff till it's done. Yeah, and it's not greedy, because picking things at random. And one way to think about why a greedy version of this won't work is the following drawing. So let's say I have 5 things. Okay? And all of these edges are dislikes. Okay? And this edge has likes. So a greedy approach will pick this, put everything in one cluster, and get a huge number of disagreements. But what you really should be doing is just putting them all in separate clusters. Or maybe putting this in one of them. So a naive greedy strategy, you just take one that has lots of neighbors and pull it away, will not work. That's why you need this kind of random process. Okay? And the reason I say it's like quicksort is because the proof of why this works is basically like a quicksort-like proof. So I'm not going to get into it. So this is of course a randomized algorithm, so in expectation. And the basic idea goes back to this thing that essentially you have these triangles that are bad. And if you get to a point where this triangle is currently intact in your graph and you have to pick one of them, you're going to pay the price for this triangle, 1 unit. Okay. If you don't, if somehow there was some other triangle you picked and you picked something else off and you pulled off something else, then this triangle disappears, you never have to pay for its cost. So in some sense you're paying for its cost only if it has survived this culling process up to this point, and then you can show that this happens with a certain probability, and basically then the probability of picking all these things is 1/3, and that's what the 3 comes. But again, I'm not going to get into detail. So yes.
So I think if
What if we have points which disagree with all of them? So they pick a point and C will be an answer.
Then you just give it a single clustering by itself. The thing is you're picking V at random. So if a random V has this property, that means lots and lots of points have disagreements, which means it's okay to do what you just did. That's what the proof says. Yes.
Is there a way to, like, once you've done this, is there a way to massage the graph and get something better?
So in fact you can. So there is a result that says if you run this first, and then run a different algorithm that basically takes a random clustering of some kind related to this, and then take the better one, you can do slightly better than 3. So yes, so it's a good point. This is clearly is floppy. You can do that. There's something else. You can, I mean, in some sense also you have to realize that the proof of why this works is masking some kind of weird LP primal dual structure. And so, in fact, another paper said, okay, why use primal dual? Let's use an SDP, a semi-different program. You can do even better. So there's lots of different technology you can use. But this is just a very simple method that gives you a reason. I should also point out, yes, sorry, you had a question.
yeah, so I think I know the proof for that. So the idea is
The n times d?
Yes.
Thank you. Tell me.
So the idea is that you have this optimal solution, right? But
Yes.
then you choose a vertex that has some number of bad edges.
Yeah.
So which was before there in that cluster?
Which is what?
Which was before in that cluster, and then you pull it here.
Yeah.
What happens is you increase, of course, some number of
Yeah.
bad edges, but you also at most can increase to n to the other ones that are there. So that's
Oh, because they're d things.
Yes.
Okay. That might very well be what's going on. Okay, that sounds about right. I can think about it, but that sounds plausible. Yeah. Okay. Yeah. So what happens if you have weights on these things? So now let's get to the case where you have min, and you have weights, and again you have. So this also requires a complete graph. I should say that this is complete. If it's incomplete, that means break. Because you're assuming I have all possible things. So if you have a weighted situation, then you have to add this extra constraint here, that the weights satisfy this property. And so then a very trivial algorithm does the following. Go from the weighted case to these +1, -1 case by doing the following. If If a wij plus is greater than wij minus, then send it to the E plus. If wij minus is greater than wij plus, send it to E plus and give it a weight of give it E minus, and then run this algorithm, the unweighted case. And if you can show that if you just do the simple trick and run this simple algorithm, you get a 5 approximation. So it's slightly worse, but it's surprising that it's not much worse, no matter what the weights are. It's kind of cool. So again, the emphasis I want to sort of make here is, the point I want to make here is that once you have this formulation, there are a couple of very simple things you can do to get a cluster. And you also have guarantees that go along with it. And you can probably do better with the guarantees, but the algorithms themselves are very simple. You don't have to do it. And there's a good sort of simple one to apply if you have data that I told. There are more esoteric algorithms, like I said, which work for the incomplete case that it gets much harder and so on and so forth. I have some notes written up that I would put on the website that talk about this, but it's a bit more involved. They're not as elegant anymore. You have to go through a lot of primal dual stuff and you get these log approximations, and it's kind of impressive. But yeah, so that's what correlation clustering is. And like I said, the main thing that I think you should take away is that it allows you to get rid of this k parameter, which is very nice. It requires very little structure in the data, but you don't have to have this plus one and minus one, and that seems to be key to making this whole thing work. And there are a couple of very simple algorithms that are greedy or greedy-like or just random that allow you to compute clusterings. Any questions? Yes.
I mean, why are we satisfied with 3?
Why not? And that's why there have been improvements. I think the best now is 11/7. I don't know, I suspect, although I don't want to promise, this problem is hard to get a p-task for. So there's some constant below which you can't go. What that constant is, I'm not entirely sure. But it's a good question.
11/7 is still better than 2, though.
Still better than 2. So I
We
think
can still do better than this
trivial one.
trivial one.
Yeah, thank goodness. Well, no, wait, hold on. The trivial one here is for max. Those are for the min. So that here you can get a p-task. Here basically problem solved. Okay. For the min is where we're still working on trying to get there. So that's where things are going to get a lot harder. So one note, Thursday we have a sort of scheduling, there's a faculty camp that's coming in also. Actually, I'm going to cancel class on Thursday and we'll just continue next week, so next Tuesday, so we have no class on Thursday. We do have a talk, one of our class attendees, Michelle, is going to be talking in the day lunch. For those of you who come to day lunch, I've always sent a mail about this. Do you want to give like a 1-minute preview of what we're going to talk about the day lunch?
Oh yeah, definitely. I would love to.
Yeah.
So this is something that you all are familiar with, procrastination. Whenever you delay something, why procrastination?
I want to look at the meeting, but I'll get to it later.
So basically you want to finish something today, but you want to delay it as much as possible. We all do that. When it comes to savings or spending, everything we want to go for immediate gratification over long-term benefit. So that is this whole area of intertemporal decision making, where decisions involve temporal aspect. So what I'll be discussing is a project where we try to find out how those decisions can be modeled in a non-Euclidean framework.
And that non-Euclidean framework allows you to reason more accurately
And make some predictions that have not been made in literature yet.
Okay. So this will be on Thursday, the day lunch. Some of you come for that meeting anyway, and for those of you who don't normally come, it's at 12:15. It's in the LCR. If you have the time, I encourage you to come in. All right. Cool.